Welcome back to section 8 of chapter 4. This is the last section of chapter 4. And in this section, we're going to be solving problems with trigonometry. So now, we've done some problem solving with trig already in the chapter, specifically with finding sides. We're going to be doing more of that, but with inverse trig, we can also start to find angles of right triangles as well. We will continue to work with right triangles through this section. We'll get into ones that aren't right in the next chapter. I have a few learning targets today. We can solve applications involving right triangle trigonometry, solve applications involving harmonic motion or sinusoidal modeling, and then answer conceptual questions involving harmonic motion or sinusoidal modeling. So, some more right triangle problems. First, we have a little bit of vocab that's not really new, but more blast from the past, back to geometry. And that's going to be the angles of elevation and depression. So now, both of these are from the horizontal. We have the horizontal, the angle of elevation. We have the horizontal and the angle of depression. The nice thing about angle of elevation, angle of depression, is that they're actually the same. If we drew another horizontal up here at the top, this angle is going to be the same as the one down there because the two horizontal lines are parallel, and so we're looking at alternate interior angles, which are the same. Same thing down here. If we drew a horizontal, that wasn't particularly horizontal, but these two would be the same. So it doesn't matter if it's an angle of elevation or depression, you can draw the triangle the same way. Now sometimes it makes sense to draw it one way or the other. Like these two both make sense for like drawn as they are. However, that doesn't always work out as well. For instance, if we have an angle of depression from a buoy, from the top of the Barnegat Bay Lighthouse, which is 130 feet above the surface of the water, is 6 degrees. Find the distance x from the base of the lighthouse to the buoy. So drawing a picture of this, the angle of depression is right here, but this triangle doesn't make as much sense because we're looking for this distance down here. We're looking for x. But knowing that these two are alternate interior angles and the same, this is also equal to 6 degrees. So then we set up a trig function. First we look at, we need to be dealing with two sides and an angle. And so we have our angle, and the two sides would be the 130 and the x. Those would be the opposite and adjacent sides. What trig function has to deal with opposite and adjacent? That would be tangent. So we have tangent of 6 degrees will equal 130 over x, opposite over adjacent. When doing these, just stick with the basic three, sine, cosine, tangent. Don't get into the other ones. There's no reason to do that. But now we can multiply, we can solve for x. So we can multiply x over, so x will equal 130 over tangent of 6 degrees. And at this point in time, it just becomes a calculator problem. Now, one of the big things to make sure of here is that you are in the correct mode. It's very possible that right now, your calculator, whatever you're using, is set to radians. We're looking at degrees, so make sure it's set to degrees. And then the tangent of 6 radians is going to be actually fairly close, but it's going to be negative. You'd end up with a negative distance. So make sure it actually makes sense too. But 130 divided by tangent of 6 degrees is going to be about 1,236.9. And then we need units. It's 130 feet, so this will be feet. So the buoy is 1,236.9 feet away from the base of the lighthouse. So that's kind of like a basic one. Now, we do have some that are a little bit more difficult. They involve two triangles. So, from the top of the 100-foot tall Altgeld Hall, a man observes a car moving towards the building. If the angle of depression of the car changes from 22 degrees to 46 degrees during the period of observation, how far does the car travel? So, drawing a picture is huge. Now, me drawing a picture on here is less good because my drawing skills are not great, and then it takes a while. So here we have the picture. But the angle of depression changes from 22 degrees, and it gets to 46 degrees, which means we have 22 degrees and we have 46 degrees. And we're looking for x. So we can write two different trig functions here. The first one, we actually look at the small triangle. So again, we have an opposite side and an adjacent side. So the tangent of 46 degrees is going to equal 100 over d. That's 1, and we can solve that the exact same way that we solved the last one. And then the other one, the big triangle, and this is where people mess up just a little bit, because the big triangle is there. So here we have the tangent of 22 degrees. It's going to be the opposite, which is 100, divided by x plus d. We need that whole side length. We can't just find the x by itself, but we can subtract. So if we multiply this first one, we can multiply the d over and divide by tangent of 46 to get d equals 100 over tangent of 46 degrees, which is just a number. We'll figure that out here in a second. This other one we can multiply over to get x plus d equals 100 over tangent of 22 degrees. Now, we're looking for how far does the car travel. We're looking for just x. So x will equal the x plus d minus d. It'll equal, x will equal the blue one, 100 over tangent of 22 degrees, minus the red one, 100 over tangent of 46 degrees. Now, both of these are just calculator things. When doing it, I mean, there's multiple ways you could put it in all together. My caution with that is to make sure that the 22 does not also include the minus 100 over tangent of 46. I generally would do them separately. Like in my calculator, I would probably go tangent of 22 equals 100 divided by that last answer equals tangent 46 equals 100 divided by that answer equals. And then I would take my two answers and I'd subtract them. Always going up into the calculator, never writing it down and then retyping those numbers. Save the values in the calculator itself. Now, if you're using something like a Desmos graphing calculator where you can type it out and see what it looks like much more precisely, you could just write this in. In fact, even the calculators have that capability at this point. I'm a little bit more old school. It wasn't quite as visually appealing back when I was learning to do it, so I do it step by step. However you do it, though, you end up with x equals about 150.9 feet again, because we're looking at the foot tall. So the car moved about 150.9 feet during that time interval. A similar looking problem We have large helium-filled penguin, because why not be a penguin, is moored at the beginning of a parade route awaiting the start of a parade. Two cables attached to the underside of the penguin make angles of 48 degrees and 40 degrees with the ground and are in the same plane as the perpendicular line from the penguin to the ground. So they're like, you can cut it and they actually look like a two-dimensional thing like this. They're not in the 3 dimensions. If the cables are attached to the ground 10 feet from each other, how high above the ground is the penguin? And so then it gives us a little diagram to show us what this kind of looks like. Sometimes, especially if the setting is kind of a complicated one, they'll give you a basic picture. Now then we'd want to label it though, and we can do things like get rid of the penguin. The penguin doesn't actually have any meaning here. So we can label. So we have an X, we have a height, because it's looking for how high above the ground is the penguin. We have our 40 degrees and 48 degrees. So we can make our 2 triangles again. We have the small triangle right here, and again we have opposite and adjacent. So the tangent of 48 degrees equals h over x, which means that the height will equal x times the tangent of 48 degrees. Then we have the other triangle. Tangent of 40 degrees is going to equal h over x plus 10. So we could multiply the x plus 10 over as well to get h equals x plus 10 tangent 40 degrees. We have a system of equations. We have 2 equations here. We can substitute. If h equals this and h equals this, that means that, I'm going to move up to the top here, it means that x tangent of 48 degrees will equal x plus 10 times tangent of 40 degrees. We can distribute the tangent of 40. Now the tangent of 48 degrees and tangent of 40 degrees are just numbers. They are not, however, pleasant numbers, so I'm just going to leave them as tangents. So we have x tangent of 48 degrees is going to equal x tangent of 40 degrees plus 10 times the tangent of 40 degrees. We can subtract the x tangent 40. So we'll have x tangent 48 degrees minus x tangent 40 degrees equals 10 tangent of 40 degrees. We could factor this x out. Tangent 48 degrees minus tangent of 40 degrees equals 10 tangent of 40 degrees. Then we can divide by that whole chunk to get x will equal 10 tangent 40 degrees over tangent 48 degrees minus tangent 40 degrees. And at that point, it's just plug it into the calculator to get x is going to be about 30.9. Now, there's going to be more decimals in there, and I'm going to use those values in my calculator. I'm not going to write them down. I wouldn't write them down on my paper. X is about equal to 30.9, but that's not what we're looking for. We're looking for how high above the ground is the penguin. We just need to plug this into one of them. I would plug it into the easier one. So h will equal 30.9 times tangent of 48 degrees. So it's the answer that we just had, times tangent of 48 degrees, gives us about 34.32 feet, yes, feet, because there's our unit, So 34.32 feet above the ground. So this one was similar to the last one, except the last one we knew what that height was. This one we did not know what the height was. We knew a different piece. So our steps were a little bit different, even though the setup was basically the same. Some navigation problems. These are ones that tend to get people a little bit. So here we have a Coast Guard patrol boat leaves Port Cleveland and averages 35 knots, which is nautical miles per hour, traveling for 2 hours on a course of 53 degrees, and then 3 hours on a course of 143 degrees. What are the boat's bearing and distance from Port Cleveland? So, starting out with drawing a picture, and then we leave on a course of 53 degrees. So, if we take that vertical line, our course is going to be 53 degrees from that vertical. And then, after a while, we are in a course of 143 degrees. And so it's looking for this angle and that distance, the bearing and distance from Port Cleveland. And it's not actually looking for that angle, it's looking for that angle plus 53, because that will be the actual bearing. So, how do we do this? Well, first of all, we can find this angle right here. That angle right there is going to be this angle plus this angle. This angle, being that these two vertical lines are parallel, is going to be 53 degrees. And this angle is going to be what's left of 143 degrees to make the straight angle. So 180 minus 143, so we have 37 degrees, which leaves us with 53 plus 37 is 90 degrees. So this is in fact a right angle, which is nice because all of our trig so far only works on right triangles. So if I wanted to clear up my drawing a little bit, it could look more like that. So notice we have our vertical lines. We have beta was 53, alpha was 37, so we have our right angle there. We're going to be looking for this angle, which will be theta plus 53, and we're going to be looking for this side. Well, we need some other side lengths, though. So let's see, the boat leaves and averages 35 knots for 2 hours. So that means they traveled 70 knots, or 70 nautical miles. And then 3 hours on the other. So 35 times 3 is going to be 105. So with that, we have a tangent of theta equals opposite over adjacent, so 105 over 70. Here we have to use inverse tangent. So theta will be inverse tangent of 105 over 70, which gives us the angle is 56.3 degrees. So we can add that to the 53, so we have a bearing of 56 plus 53 is 109.3. And then for this, the distance away, this x, we can use Pythagorean theorem. X squared equals 70 squared plus 105 squared. So square them, square root, x will be equal to about 126.2 knots. And so this one, like the problem itself, was not too bad. It's the setup that people struggle with there. So make sure you get the setup. Notice we also use the inverse trig here, and making sure we give an answer of the bearing and not just that angle. Those are the things to watch out for on that type of problem. Another thing we can use these trig applications for is simple harmonic motion. And simple harmonic motion is things like the height of a clock hand, it goes up and down, wheels, springs, pistons, anything that goes back and forth, back and forth, back and forth, or up and down, up and down, up and down, consistently the same. And what they can do is they can be written as a sine or cosine function. And a fairly, I want to say a fairly easy one. There's not as many variables here as a lot of times there could be. We don't have any phase shift. We don't have any vertical shift. It's either the distance equals a times sine of omega t, or distance equals a times cosine of omega t. And a lowercase omega looks like w. You can think of it as w if you want. Where a and omega are real numbers, where it's greater than 0, the motion has frequency, omega over 2 pi, which is the number of oscillations per unit of time. So the frequency could be so many things per hour, so many things per minute, so many things per second. It depends on the problem. So what does this look like? A mechanical linkage, like the one shown here, which is a wheel with an 8 centimeter radius, turns with an angular velocity 8 pi radians per second. So what is the frequency of the piston in cycles per second? And then here we also have an equation here. It's 8 cosine of 8 pi t. But if the angular velocity is 8 pi radians per second, how many times does it go around the circle per second? The circle's only 2 pi, so it would be 8 pi over 2 pi, which is exactly what this is, which is 4. So the frequency is 4 rotations per second. And then what is the distance from the starting position? Exactly 3.45 seconds after starting. Well, we have our d of t was 8, and that 8 is from the radius cosine of 8 pi t, and that 8 pi is from the 8 pi radians per second. So the amplitude is because it's an 8 centimeter radius, and the 8 pi t is because of the angular velocity. So we can find d of 0, which when you plug in 0 to t, you get 8 times cosine of 0. Cosine of 0 is 1, so that's just 8. And you can plug in 3.45, so you get 8 times cosine of 8 pi times 3.45. And this is going to be in radians, by the way, so you have to make sure your calculator, again, is in the right mode, because you are going to be using your calculator for this. This is not one where you would just know what this value is. But it does come out to be about 2.47. And it's asking what is the distance from the starting point? So this is going to be position. So it starts out at 8, it ends at 2.47. So the distance from the starting point, we just have to subtract to get about 5.53 centimeters away. So it is 5.53 centimeters away. Now that does not mean that it moved 5.53 centimeters. Because it went around the circle a few times, being that it's going around 4 times per second. It's just, this is how far, it's the displacement. So every let's see, it's 4 rotations per second, so every quarter of a second, it makes a complete rotation, and it's 0 away from the starting point. So notice, again, this is not how far it moved, this is how far away it was. Another big example of simple harmonic motion is springs. So with a spring, it would start here, like that would be 0. It might or may not start there. That's actually probably equilibrium. If you just had the spring sitting there, that's where it would sit. If you pull the spring down 5 centimeters and let go, it then goes 10 centimeters up, so it's above 5 centimeters, and then it'll go back down, then back up, and then back down, back up. I know that in reality, it will eventually slow down and go towards equilibrium, and that would be like a dampened harmonic motion. But for the sake of these types of problems, we have assuming perfect elasticity and no friction or air resistance, so it will keep moving the same way in perpetuity. It won't slow down or stop or anything like that. So if the weight is displaced a maximum of 5 centimeters, find the modeling equation if it takes 2 seconds to complete one cycle. So the first thing we have is it's being displaced 5 centimeters, which means the amplitude, both distances, is going to be 5. So we know that the amplitude is going to have to be 5 here. Now, if it takes 2 seconds to complete one cycle, that means the frequency, how many cycles it completes per second, is going to be 1/2. So that omega over 2 pi is going to equal 1/2, because we have to find the reciprocal of the time it takes. The reciprocal of the period is the frequency. And so for this, we can find omega, multiply by 2 pi, we get omega equals pi, which means we can plug it in. Now, do we want to use sine or cosine? Well, that just depends on where your starting point is. Let's have our starting point be right in the middle. So it'll start at 0. So our distance will equal 5 times sine of pi t. And that's all it does. I mean, there might be multiple parts of this problem asking you how, like, where's the position at time t equals 1.3. And at that point, you just plug in 1.3 and you can find it. This we're looking at setting up the equation. So that is it for this particular section, last section of the chapter. So I will see you in class, but until then, keep working problems, keep asking questions, and as always, happy mathing.